All right, guys, this is your lesson on gravity and tides, and this is your bell ringer before we get started. So these are the questions we are going to be answering in our lesson today, but I do want to see what you already know before we get started. So do me a favor, go ahead and pause the video, and I want you to answer these questions for me. All right, now that you've had a chance to write down some answers to these questions, let's think about this. Some of you might already know what causes our tides. Some of you might know that it has something to do with the moon or something to do with gravity, but we are going to dig in and talk a little bit more in depth today, okay? And so for how many high and low tides we have each day, we actually have 2 high tides and 2 low tides each day. We'll talk about why that is when we're going through these notes. And the last question, it says, do the moon phases have anything to do with our tides? Yes, they do, and we'll talk about how they're connected later. So specific moon phases can tell us when we have a specific kind of tide. All right, so this is the title for your notes. If you are copying down any notes or you just want to have a space where you can write some notes about gravity and tides, go ahead and title it Gravity and Tides. That way when you go back to study, you'll know what you're looking at. All right, so we are going to talk about gravity first. Gravity is the force that holds everything in the universe in place. It acts between all objects in the universe, even my laptop and my desk. There is gravity between those 2 objects. Now, gravity depends on the mass of the objects and how close they are to each other, okay? So if it's a really small object and it's really far away, it's not going to affect us. But if it's a really big object and it's far away, it can still affect us. If it is a really small object and it's nearby, it can affect us a little bit. And if it's a really large object and it's really, really close to it, it's going to affect us a whole lot. Okay? So down here, the last bullet, if the objects are closer, gravity is greater. And if the object is larger, that gravity is going to be greater. All right, so now let's talk about how that affects orbits. All right, so gravity is the force that keeps everything in orbit. So everything we talked about that's in the universe, gravity is what's keeping it where it is. Okay? So now we're going to talk a little bit about how things react to gravity. So think about the moon. Okay, if the gravity of Earth was too strong, it would pull the moon into the Earth and we would collide. Now, that would be absolutely awful. That would be completely devastating. It would probably kill everything here on Earth, but that's not going to happen. Not anytime soon, anyways. It's not moving towards us or anything. Technically, the moon is actually moving farther away from us. So we're safe from the moon. That's just an example. And if the gravity is too weak, the object is going to fly past. It's going to keep going. It's not going to start orbiting Earth. All right. So if we talk about an asteroid, it's going really, really fast, or if it's far enough away from Earth that it doesn't really feel our gravity, then it's just going to keep going. It's not going to affect us, and we aren't going to affect it. Now, if an asteroid came in at the exact right angle and had the exact right speed and was exactly close enough or far away from the Earth, then it would be able to begin orbiting Earth just like the moon does, okay? So when we talk about things orbiting, it is a very delicate balance. So it can be knocked off, but it's not going to, one, because the objects are so huge, and there's not really anything that's gonna come around and knock things off their orbit unless there is some kind of disaster that happens. Now, I'm a scientist. Everything is technically possible unless we can prove that it is impossible. So it's not impossible that there's going to be an asteroid that comes around and hits us at some point, but it's not something that's likely to happen in the near future. NASA looks out into outer space and kind of watches and looks for things that are headed towards us. And right now, there's not really anything that's coming towards us that could hurt us, okay? So I'm not trying to freak you out, but I'm just saying there are possibilities, and that's what I'm talking about in this lesson, okay? All right, so the next thing, we need to talk about weight versus mass. All right, they are not the same thing. They're close to each other. They're connected, but they are not the same thing. So weight is the measure of gravity on an object, okay? So if something has really, really strong gravity acting on it, its weight is going to go up because that gravity is pulling on it more. So if we talked about, actually, we'll talk about it on the next slide. We'll talk about your weight on different planets. We'll talk about why that would be different, okay? All right, and then mass is the amount of matter that's in an object, okay? So if we think about something that's really, really dense, like a bowling ball, that has a whole lot of mass to it. But if we compare that to a basketball, they're roughly the same size, but the basketball has less mass, okay? So the basketball doesn't have as much matter in it, so it has less mass. And you're going to measure mass with a balance. So you would take that balance and you would take something that has a known mass and you would compare those masses on the balance until you figured out what the mass is of the other object that we don't know. All right. So now let's talk about the gravity on other planets, okay? So first thing I want you to notice is that mass stays the same on every single planet, and that's always the case, okay? Now, if you lose an arm, your mass is going to go down, or if you lose weight or gain weight, your mass is going to change. But for this comparison here, this is the exact same person on each planet, and he has not gained or lost weight. We're just comparing his weight on the Earth to his weight on other objects in outer space, okay? So mass stays the same across all of these objects. Earth, let's look at this one first. This is something we already know. His mass is 70 kilograms, and his weight in newtons is 686.4, and his weight in pounds is 154.3. So if he weighs 154 pounds or about on Earth, then if he's on the moon, he's only going to weigh 25 pounds. And that's because the moon has so much less gravity than the Earth does, okay? So it's got less gravity. That means his weight is less. But I want you to see up here that his mass has still stayed the same. All right, now if we hop over here to Jupiter, Jupiter's a lot bigger than the Earth. So his weight on Jupiter is 364.8 pounds. That is a lot more than what he weighs on Earth because Jupiter has so much more gravity because it is so much larger, okay? So when we talk about your weight on different planets, your weight is what's changing, even though your mass, the amount of matter you have in your body, stays the same. So your weight is just a measure of gravity. That's why it changes depending on what planet you're on. All right, now we get to talk about gravity and tides. Now, the gravity that causes our tides is from the moon, all right? So the moon's gravitational pull on Earth is what causes us to have high and low tides, and it causes those changes in our high and low tides, okay? So the moon's gravity pulls a tidal bulge around Earth, so it looks like this thing down here on the diagram. So I've got some pictures on here to show you what I'm talking about, okay? The sun has some effect on our tides, but it is very little compared to the moon, and we'll talk about what that looks like in just a second. So first thing, high tides occur at the same side of the moon and on the opposite side of the moon from Earth, okay? So we're sitting here on Earth. High tide is going to be over here right at the moon and on the opposite side of the moon. Now, that's because the water kind of acts like a rubber band. If you pull a rubber band, let's pretend like there's a rubber band around Earth. If I pulled that rubber band all the way over here and I let it go, it's going to fly to the other side. So the force from this rubber band, or let's say the water on Earth, once it gets out of the moon's gravity, is going to go straight back and head this way to this side over here, okay? So it's the same idea with the rubber band. If I pulled that rubber band out to here and let it go, that force is automatically going to go to the opposite side of Earth, all right? So we have a high tide on the same tide as the moon and on the opposite side of the moon. Now, we need to pretend like we're talking about almost like we're talking about a square here. So we've got one side over here nearest the moon. The second side is opposite the moon. So those are the two sides where we have high tides, and the other two sides that are left are where we're going to have low tides on Earth, okay? So high tide is always right here. Low tide is going to be at a right angle from our high tides, okay? So now let's talk about the different kinds of high and low tides we can have, all right? A spring tide is a higher than normal high tide because the gravity of the sun and moon are pulling along the same line. So not only is the moon pulling on that rubber band, it's pulling on the water, the sun is pulling in the same direction. So they're making this high tide just a little bit higher, and that in turn makes this high tide a little bit higher. Now, if we think about it again, still with our rubber band analogy, when you stretch the rubber band out, you have less right here on these edges. So your low tides are actually going to be a lot lower than they would normally be, okay? So this happens during our new moon phase and our full moon phase, okay? So we have a high tide over here that's really, really high. We have a high tide over here that's really, really high. Whoops. And we have a low tide up here and down here that are going to be a little bit lower than normal. So those are spring tides. They're going to be extra high. So an easy way to remember that is if you watched Winnie the Pooh at all, you can think about Tigger. His tail, it's spring. He bounces really, really high. So that makes our high tides just a little bit higher than normal. All right. And the next kind of tide is a neap tide. So neap tides are going to be higher than normal low tides. Okay, so our low tides right here on the sides away from the moon, our low tides are going to be a little bit lower than normal, and our high tides are going to be lower than normal. Okay, so since the sun and the moon are not working together in this case, the sun is pulling in this direction, it's pulling at a right angle compared to the moon's gravity. We're going to have a little bit higher low tide, and the high tides are actually going to be lower. So the sun, moon, and earth make a right angle. Their gravity is pulling along perpendicular lines. So no longer are they working together, they're kind of working against each other. Okay, so if we think about this kind of like net force, there's less net force pulling on the moon right here or pulling on the tides right here because the sun is pulling in the opposite direction. So we've got to think about it like that. Okay, and this happens during our first quarter moon phase and our last quarter moon phase. All right, so this is your lesson for gravity and tides. You can always come back to use this to study to help you remember what's going on, or if you just have questions or you want to hear it again. Okay, so that is your lesson on tides.